Hello and welcome back to Calculus 1, section 5.3, Fundamental Theorem of Calculus. This is a short section where we take a look at Fundamental Theorem of Calculus. Theoretical results. So, part 1, you already know. And that is the good old definite integral a to b of f of x dx is equal to any antiderivative capital Fx from a to b, which is computed as f of b minus f of a. So this formula you guys learned in 5.2. And this is the part 1 of Fundamental Theorem of Calculus. And in this formula, what is important is to understand that this particular integral can give you area under the curve as long as the function is always positive. If the function is negative on any of the intervals, you have to use the absolute value around the negative part so that you can get the correct area. So, if f of x is always larger or equal than 0, then area equals the definite integral. If f of x is, let's put it this way, if f of x is less than 0 on any part of interval AB, then area is not equal to the area under the curve. And the example which I listed the last time was the area under the sine curve. So if I draw sine curve, 0, pi, 2 pi, the area would be integral 0 to pi of sine x dx, which is this area here, plus the absolute value of the integral pi to 2 pi of sine x dx in absolute values, which is the bottom part. And then if you insert calculations here, as we saw last time, you will get 4, right? Knowing it's a positive. So the first part of the fundamental theorem of calculus is just a definite integral calculation, and this knowledge that area under the curve can be represented with the definite integral if you have this function to be above x-axis for all times. Now, part 2 is the one that we are focusing on now, and the part 2 says that the derivative of the integral a to x of f of t dt is equal to f of x. So this is the one that it's new and it's important, hence fundamental, right? So what's such a big deal about this formula? Well, if you take a look at just for a second at your previous problem, you see that within the interval you have a lowercase f, which we keep for as a function, right? And then later, to calculate everything, you are using capital F, which is denoting antiderivative. Now in the part 2, what you see is a lowercase f and another lowercase f. So technically, what you did is you changed the variable from t to x. It's the only thing that happened. right? Because lowercase f is the lowercase f. If I have that f of x is equal to x plus 3, then f of t is t plus 3. Then f of 7 is 7 plus 3. The f of a heart is a heart plus 3. So whatever goes into that, right, you don't get to change the shape of the equation. It is something plus 3. Now you can define a different function, g of x, that will be maybe, I don't know, x divided by the square root of 1 minus x squared. Different function for a different letter, right? And if I use capital F, that means antiderivative, so that will be x squared over 2 plus 3x plus c, right? So antiderivative of x plus 3 is this. So what you see in the part 2 of the fundamental theorem of calculus is that these two are the same function. They just have a different variable inside. So you might say, well, what's the point of writing that the function is technically equal to itself if I just change the variable? Well, this is actually the key of Calculus 1. The entire course that you've seen so far culminates in this particular formula, right? So what is this all about? Well, if you do the calculation, you will see, because it's quite easy to do the calculation, you see that you get f of x. Now, my question to you to think, by the time I'm done with this, is what is this formula trying to tell you? What is this formula for? So now, copy the derivative. The integral of f of x, we know it's an antiderivative of x computed from a to x, which is the derivative of, oh, sorry, it's supposed to be a t. There we go. So this is f of x minus f of a. Now f of a is a number, so when you take the derivative, antiderivative, you get the function back, but now it's in terms of x. Minus 0 is just f of x. So this is the way for us to just confirm that this calculation makes sense. So all I did is a basic definite integral. So now, when I have this, what do I do? Like, what? Why? What is going on over here? What is this? What is this formula actually telling us? If you consider that you put the function in and you get the same function out, what is the formula trying to tell you? It's probably the obvious thing you are thinking about, you're just not saying it. So just say it. Anyone? Well, how about the derivative integral just cancel and that's it? Right? That concept that one undoes the other is pictured in this formula. They are opposite operators. You literally cancel them out and you get the same function on the other side. That's all it says. So we spent 2 chapters on derivatives. We spent 1 chapter so far. Another 4 are coming up for you guys in Calc 2 on integration. And this formula just says one is the opposite of the other. And the last question is, y. So let's take a look at formulas. The derivative, if you remember the limit definition, h goes to 0 of f of x plus h minus f of x divided by h, and Riemann sum for definite integral a to b of f of x dx, which gave you the limit n goes to infinity, summation 0 to n of f of ci delta x. So what is what are the aspects of this that make them opposite from each other when you look at these formulas? And it's quite obvious, may I add. Anyone? What's different between these? No takers? Just state the obvious. What's different between the formulas? I'll wait. State the obvious. What is different? There are three obvious things and one that is kind of hidden. Okay, correct. And what else? Yes, thank you. Holy nightmare, took forever. So derivative has a division, and this one has multiplication. That's opposite. And then there's a subtraction here, and there's addition over there. So all of the, and then 0 and infinity, people like to point that as well because it's obvious. So clearly, right, they use all opposite operations, so they are all opposite of each other. Good. So, so now what is the derivative of integral from 3 to x of cosecant x cubed dx, whatever, I mean t dt? You just get, that's an arrow, cosecant x cubed, and you just move along. That's all it is. It's very simple. Just rewrite the function with x instead of t. Done deal. Bye.